Okay, so in this video we want to have a look at the graphs of exponential functions. So an exponential function is one in which the variable is in the exponent. So we've seen functions of this kind of form before, y equals x squared, y equals x cubed, y equals x to the power of 4. Those are polynomial functions, but they have x in the base. Exponential functions would be, for example, y equals 2 to the power of x, or y equals 3 to the power of x, or y equals 4 to the power of x. So the most basic exponential functions are of the form y equals a to the power of x, and then we'll get this function right, and then we'll look at applying our transformations to that particular function. So an exponential function y equals a to the power of x, but only where a is a positive real number other than 1. For example, so i.e. in the notation we've covered in our most recent topic, r plus excluding 1. And that's because if our a was 1, for example, we would have y equals 1 to the power of x, which is just y equals 1. So that's not an exponential function, that's a horizontal line through y equals 1. Similarly, if y were to equal 0, it'd be y equals 0 to the power of x, which is just 0. That's a horizontal line on the x-axis. Okay. If a was to be a negative number, for example, negative 2 to the power of x, the problem we would have is that depending on whether x was an odd or an even number, so if x was 0, negative 2 to the power of 0 is 1. If x was 1, negative 2 to the power of 1 is negative 2. If x was 2, negative 2 to the power of 2 is positive 4. And so you're going to get a graph that oscillates and gets bigger. Okay, so by definition, not an exponential function. Okay, so the base of the exponent has to be a positive number, and it can't be 1. It could be a fraction, okay, and we'll have a look at that, but it can't be negative. Okay, let's have a look then at two examples of exponential functions. Let's have a look at y equals 2 to the power of x and y equals 10 to the power of x. So let's just think about plotting some table of values to sort of think about what's happening with this function. So let's start in the middle. When x equals 0, 2 to the power of 0 is 1. When x equals 1, 2 to the power of 1 is 2. When x equals 2, 2 to the power of 2 is 4. When x equals negative 1, 2 to the power of negative 1 is 1/2. When x equals negative 2, 2 to the power of negative 2 is 1/4. Thinking about 10 to the power of x, same thing. Start in the middle. 10 to the power of 0 is also 1. 10 to the power of 1 is 10. 10 to the power of 2 is 100. 10 to the power of negative 1 is 1/10. 10 to the power of negative 2 is 1/100. Okay, so if we think about plotting those graphs, let's think about 2 to the power of x first. So y-intercept at 0. When x equals 1, y equals 2. When x equals 2, y equals 4. When x equals negative 1, y equals 1/2, 1/4, etc. Okay, and so we can join them up and we get this. Sorry. And then obviously when x equals 3, y would be 8. So we're sort of heading, we're starting to head up, quite high at this point. Sorry, it's a slightly wobbly exponential graph. So y equals 2 to the power of x. If we were to draw y equals 10 to the power of x on the same axes, so we know it also has a y-intercept at 1. That's the thing that's the same. When x equals 1, y equals 10. And when x equals 2, y equals 100. So obviously it's way off the charts. And they're going to have, 1/10 and 1/100. So tiny. So it's going to be much closer to the x-axis here. Same y-intercept here. And then much further away from the x-axis up here. Okay, getting steeper and steeper and steeper. So we get this more extreme shape, the larger the base. Okay, so more extreme in that it gets closer to the asymptote or the x-axis really quickly, and it also then veers away from the asymptote really quickly as it's getting bigger and bigger. Okay, so for example, if we were to draw y equals 8 to the power of x, it would be somewhere in between these two things. So, below the blue graph but above the green graph down here, below the green graph but above the blue graph up here, something like that. Okay. Alright, so we've got our sort of basic shape. We've got this sense that this is what we're dealing with here, this exponential growth, so increasing slowly at first and then more and more quickly. We also note that as x gets more and more negative, the function gets smaller and smaller and smaller, but it's never actually going to get to 0. If you've got, a number to the power of negative 50, so it's going to be 1 on a to the power of 50 versus negative 100, so 1 on a to the power of 100 versus a to the negative, a million. Okay, this is getting very, very small, but it's never going to get to 0. You're just getting a larger and larger and larger denominator, so a tinier and tinier and tinier number, but it's not actually going to get to 0. So we have an asymptote, okay? So the x-axis is an asymptote here. There is no vertical asymptote. It's continuing to get big, it's continuing to get small, okay? There is just the horizontal asymptote at y equals 0. So remembering, if that moves at all, we're going to need to draw a dashed straight line and label it with an equation. So the things that all our exponential graphs have in common, if we have y equals a to the power of x, it goes through 0, 1, it goes through the point 1a, and it goes through the point negative 1, 1 on a, just as some touch points to get a sense of the shape. Okay, so in the previous example, which we talked about in class, we had an example where we had a decreasing exponential graphs, as shown at on the right, and that was because the equation we were looking at had a fractional base, okay? So we had a fractional base, which was, for example, half to the power of x. So let's say y equals half to the power of x. And so that meant as x got bigger and bigger and bigger, the value of y got smaller and smaller and smaller. So we had the graph going in the opposite direction. And we talked about at that time that this equation can be written as 2 to the power of negative x. Okay? And that fits with what we are thinking if we think about this as a transformation. So if this is y equals a to the power of x, then this graph over here has been reflected in the y-axis. Okay, so the transformation that's occurred to create this shape is a reflection in the y-axis. Now we know from our previous studies of these transformations that if we reflect a function in the y-axis, it becomes f of negative x. So if my function is a to the power of x, it's going to become a to the power of negative x. So when we have that negative x in the power, we get a reflection in the y-axis. So here on the graph opposite, label the unlabeled graph with its rule. This is a to the power of x reflected in the y-axis, so it will be a to the power of negative x. If we then think about our other reflections, that's the first thing I want you to think about when you're looking at an exponential graph. Have there been any reflections? Hence, which way up does my graph go? So in this first example on the left here, that's the graph of y equals a to the power of x reflected in the x-axis. Now we know when we reflect in the x-axis, f of x becomes negative f of x. So in this case, a to the power of x will become negative a to the power of x. I want to be clear about the fact that negative a to the power of x isn't the same as negative a all to the x. Okay, so this is, instead, we think about negative a to the power of x is negative 1 times a to the power of x. So we have a reflection in the x-axis. And the equation will be y equals negative a to the x. The graph on the right, we've got reflections in both axes. So we want to combine together both reflections, and our equation is going to be negative a to the negative x, reflected in both the x and the y-axes, and we would get that shape. So as I said, that's the first thing I want you to think about. Which reflection have we got? Which reflection or reflections are happening, and hence what's the shape we're dealing with here? Okay. Then we want to think about our other transformations, dilations and translations, yeah. So we know that when we multiply the whole function by a number, so k times a to the power of x, that is, for instance, essentially what we're saying here is f of x becomes k times f of x, okay? So that is a dilation by factor of a from the x-axis. So all of the y coordinates are getting multiplied by, sorry, not a factor of a, factor of k, from the x-axis. So all of the y coordinates are being multiplied by k. We know in this instance this is equivalent to saying, well, f of x has become f of nx. So that's the dilation from the y-axis. But we know when we dilate from the y-axis, it is by a factor, of 1 over n from the y-axis. So as we make n bigger, the graph gets squashed in towards the y-axis. Okay, when we're adding or subtracting onto the x, so this is equivalent of saying, well, f of x is becoming f of x plus or minus b. Okay, so these are translations to the left or right. Oops, sorry. So, for example, if we had 2 to the power of x plus 1, that would mean that we have gone to the right, sorry, my apologies, to the left by 1. So again, when it's adding or subtracting just onto the x, it's the opposite of what you think it should be. It's the same for the dilation from the y-axis. If we had 2 to the power of x minus 3, it would be 2 to the power of x translated to the right by 3. Okay. And this last one here, y equals a to the power of x plus or minus c, so that's equivalent to saying we've got a function and it is becoming that same function plus or minus a number. So that is when we are translating, translation up or down. For example, if we had 2 to the power of x plus 2 or 2 to the power of x minus 4, this would be up by 2, 2 to the power of x up 2, and this would be down by 4. So 2 to the power of x down by 4. So we want to identify those transformations. Noting that this one here, if we move our graph up or down, that's going to translate our asymptote. So that's one of the first things we want to think about too. We want to think about the shape on the basis of the reflections, and we want to think about translating the graph. And we want to think about whether or not whereabouts the asymptote is, so that then we can think about drawing in our shape and calculating any relevant intercepts. Okay, so let's have a think about these examples. So sketch the graphs of 3 to the power of x, 1/3 to the power of x, and 2 times 3 to the power of x on the same set of axes. So we'll draw y equals 3 to the power of x, and then we want to think about how the other two graphs connect to that. I'm just going to shrink this down so I can fit the whole axes on the screen at once. Okay, so y equals 3 to the power of x. Let's draw that in first. So when x equals 0, y equals 1. When x equals 1, y is 3. When x equals 2, 3 squared is 9. When x equals 3, 3 to the power of 3 is 27. And after that, we're going to be off the chart. And then down here, things are going to get small quite quickly. So we're going to have a third, a ninth, 1/27th, etc. Okay, so... So quite close to the axis. Pretend that goes through there. Okay, so that's y equals 3 to the power of x. Okay, let's think about y equals 1/3 to the power of x. So we know that 1/3 is the same as 3 to the negative 1. And so this is the same as 3 to the negative x. Okay, so this means it is our blue graph reflected in the y-axis. So we're going to take the blue graph and we're going to mirror it over the other way. So the y-intercept will still be at 1. At negative 1, it'll be equal to 3. At negative 2, equal to positive 9. Negative 3 equal to positive 27. And then down here, 1/3, 1/9, 1/27th. Okay, so we want to draw in our shape. Okay, so our purple graph is y equals 1/3 to the power of x. And then finally the last one is y equals 2 times 3 to the power of x. So this is a dilation by a factor of 2 from the x-axis. So when we dilate from the x-axis, all the y coordinates are being doubled. Okay, so for example, instead of going through 0, 1, it'll now go through 0, 2. We're doubling the y value. Instead of going through 1, 3, it will now go through 1, 6. We're doubling the y value. 2, 9 will now become 218. We're doubling the y value. 327 becomes 354 and is way off the chart. Now, unlike when we change the base of the exponent, we're dilating from the x-axis, by a factor of 2, so all the y values are doubling. So also down here on the left-hand side of the y-axis, we know that when x equals -1, y equals negative a third, and y equals positive a third, and so when we double 1/3, we get 2/3. When we double 1/9, we get 2/9. When we double, 1/27, we get 2/27. So the whole red graph is going to sit completely above the blue graph. Okay, and it's hard to get that sense of scale here. The scale's too small down there for us to see it clearly. But that idea that they don't actually cross over at all. The red graph is completely above the blue graph. So this is y equals 2 times 3 to the power of x. Okay, so obviously if you have a grid you need to be precise, but otherwise you really just want to get that sense of the base of the exponent doesn't matter so much. It is about shape, transformations, where's the asymptote, and then you'll calculate x-intercepts, y-intercepts, or any other relevant points to make sure that, and then the base of your exponent or anything else will be actually reflected in those points. So for example, this graph here, y equals -10 to the power of 2x. So we're starting with 10 to the power of x. Okay, it's y equals 10 to the power of x, reflected in the x-axis. That's the negative out the front. So that means the shape is going to go this way. Okay, and it is dilated by 1/2 from the y-axis. So it's going to be squashed in a bit, but if we're not drawing two graphs on the same axes, it's hard to actually show that. We'll simply show that by calculating points. So we'll calculate a couple of points here. Obviously it's going to cross the y-axis, so we need our y-intercept. So we let x equals 0, -10 times 2 to the power of 0, so that's 0. So -10 to the 0 is -1. Okay, remembering different to -10 to the 0 doesn't equal -10 all to the power of 0. It would have to have those brackets. It instead equals -1 times 10 to the 0. So -1 times 1. Okay, so we've got our y-intercept. We're going to need another point. So perhaps we'll have a look at when x equals 1, for example. We're going to get y equals -10 to the power of 2. So that is -100. So we're going to have, there's a couple of points to think about. We've got 0, -1 for our y-intercept, 0, -100. So it's going to be difficult to show that scale precisely, but we do want to get the sense that the graph gets steep very quickly. Our asymptote hasn't moved. The only thing that would move the asymptote would be translation up or down. So the x-axis is still our asymptote, so we don't need to draw in anything separate. And we're going to have quite a steep graph. Steep for two reasons, both because of the base of 10, which is very steep, and also because of the dilation by half, which also made it even steeper. So 0, -1 for our y-intercept, and obviously this scale's not correct, but a sense that it is a long way away. Sorry, not 0, 1, -100. Sorry, I made that mistake over there. Okay, so you want to have at least 2 points on your exponential graph, so your asymptote and 2 points. So if you've got 2 intercepts, you don't need any additional points, but if you've only got 1 intercept, like we do here, only a y-intercept, then you'll need to calculate an additional point. Okay, example 3. Sketch the graph of y equals 2 to the -x plus 1. Okay, so this is y equals 2 to the x, reflected in the y-axis. So the shape is going to be going this way, okay, and translated up 1, okay, which means that we're going to have the asymptote at y equals 1. Okay, so we're going to have, the whole graph sitting above that asymptote, y equals 1. So dashed straight line labelled with equation. So we're going to have a y-intercept. Let's calculate that. So our y-intercept is going to be y equals 2 to the 0 plus 1. So that's 1 plus 1. So 2. So y-intercept at 0, 2. So now make sure you maintain your scale. Okay. So this distance here you've made 1, and so therefore you want to have, if your y-intercept, sorry, is at 2, it needs to be that same distance again above here. So that's going to be my y-intercept. I'm going to need another point. So maybe when x is -1, just because otherwise we'll have fractions. So we've got y equals 2 to the power of -1, so that's +1 plus 1, so that's going to be 3. So we're going to have -1, 3. Okay, and then we want to draw in our shape, decreasing exponential because of the reflection in the y-axis. So y-intercept at 0, 2, x-intercept at -1, 3. Sorry, not x-intercept, another point at -1, 3. 2 points plus your asymptote. Done. Okay, number 4. Sketch the graph of y equals 4 to the power of x plus 1 minus 2. Okay, so this is y equals 4 to the power of x, translated left 1, and translated down 2. Okay, so that's going to tell us about our asymptote. There's no reflection, so the standard exponential shape, down 2. So y equals -2 is my asymptote. Let's calculate our, now because our graph's going to go this way, we're going to cross the x and the y axes, but we don't know whether it's going to be over here, whether it might actually go through the origin, so we can't draw it in until we've calculated our points. So our y-intercept in this instance is going to be y equals 4 to the power of 0 plus 1, so it'll be 4 to the 1 minus 2, so that's going to be 2. So our y-intercept, now again, consistency with your scale, this distance here is 2, and so if your y-intercept is also at 2, it needs to be that same distance above the x-axis. Okay. Now we're also going to cross the x-axis, so we need to calculate an x-intercept here. And we'll go into solving these equations a lot more over the next few lessons, so I'm not going to give you many with an x-intercept for now. But let's have a little look at this, because you should have done this before and it should be somewhat familiar. So you want to focus on an exponential equation if you can, writing both sides or everything in the equation with the same base. Okay, so I've added 2, and now I'm going to focus on, well, 4 is 2 squared. And then when we have a power after a power like this, we multiply them together. So that's 2 to the 2x plus 2 equals, and this is 2 to the 1. Okay, so this tells us that 2x plus 2 equals 1. So that is equating the powers. And from there, 2x equals -1, so x equals -1/2. Okay, so x is -1/2, and so then we want to draw in our exponential graph. Okay, so we've got 0, 2 for our y-intercept, we've got -1/2, 0 for our x-intercept, and your asymptote. A little box here about sketching exponentials using your CAS, no different to sketching any other graph. Enter in the equation. Again, to note that it doesn't actually draw in the asymptote. So, you know, if you suspect an asymptote at y equals 1, perhaps you could draw the line y equals 1 to see whether that looks like that's an asymptote. But really, you're going to need to rely on your understanding of the function to know that when you translate this graph onto paper, you need to draw in the asymptote. Work today is from a worksheet, Graphs of Exponential Functions.